Alrighty, Pchem, we are back with our last way to calculate enthalpy by just using enthalpy. There's actually one more way, if you can believe it, that deals with something called Gibbs free energy and entropy. But if we're talking about strictly enthalpy, this is the last way to calculate it. And it's by using our bonds in our chemical reaction. So we're going to kind of revisit Lewis structures a little bit with this, which I'm sure you're thrilled about. And we'll kind of talk about that a little bit. But it's, I promise, our last way of enthalpy only, calculating enthalpy. So just as a quick review for you, when we talk about our chemical reactions, we've talked about this a couple times now. When we start a chemical reaction to get it going, we generally need to break some bonds to make that happen. And every time we break some bonds in either an exothermic or an endothermic process, we got to put a little energy in to make that happen. And every chemical reaction has an endothermic part where those things break apart. And then we get energy out on the back end when they reform. So if you remember, we have that kind of activated complex at the top here where we have our activation energy that goes in and then it turns into that kind of combination of new things. That breaking of a bond requires energy, and when you make the bond again, you're taking something from its highest energy state at that activated complex and you're putting it back together and releasing that energy. So energy in to break a bond, energy out as you make new bonds. And again, just as a gentle reminder for you, the difference between those two things is the enthalpy. If you start with less energy and end higher, and I think I'm doing this backwards, okay? That means you're going to have an endothermic reaction. And if it's the opposite, where you end lower and you start higher, then you are going to have an exothermic process. Now, if you think about how that happens, it happens because every single bond, or most bonds between chemicals, are broken in a chemical process. You know, you get some breaking that's happening. And in enthalpies that are calculated using bond enthalpies, what they've done is they've analyzed the energy in breaking each individual bond here. And it's an average energy because we've kind of talked about before in like polarity and stuff like that, depending on how the molecule you're looking at is connected, the energy it's going to take to break something might be a little bit different. So what we're looking at generally is an average energy it takes to break a specific bond. And what you need to be good at with a bond enthalpy calculation is you need to be good at knowing what the structure of your compound looks like so you can analyze what is going on with it as it's breaking. So for instance, let's say I'm going to be breaking apart this molecule here, which is acetic acid. It's the stuff that makes a vinegar. And I want to break this apart. What I need to do is I need to be able to either draw the Lewis structures, what they typically like you to do, because then it ties the two concepts together, or they're going to ask you to take a look at the Lewis structure and then analyze it and pull it apart. And the most important part with this is being able to count. And you might kind of laugh at that, but you have to be able to count every type of bond that's there and and how many of each of those bonds that are in there as well. So in this particular molecule, if you take a look at it, we got to look at each single connection here that's in this molecule. And that's why usually they pick pretty simple molecules, because you wouldn't want something gigantic like, let's say, like sucrose, which is this massive molecule. You're not really looking at something big like that. They're going to keep our molecules pretty simple because you have to be able to do this exam, you know, not in 8 hours. So when you look at this molecule here in this example, I want you to take a look and see if you can figure out how many different types of connections you have in here. Let's see, hopefully I didn't forget any of them, okay? So if you want to pause, you can. Otherwise, you can just keep going. Like I said, we'll hope I didn't screw this up. So if you look here, I have 3 C to H connections. I have 1 carbon to carbon connection. I have 1 carbon to oxygen double bond, 1 carbon to oxygen single bond, and 1 O to H. And depending on what I'm making, I might have to break each of these individual bonds to make my product. And so it can be a lot of energy that has to go in because I've got to rip all of these guys apart. And so when we do reactions and try to figure out their enthalpy change using the bonds, what we have to do is we have to take a look at how many bonds we're breaking and then figure out how much energy it takes to make all of those broken. And then we've got to think about the new stuff that we're forming and then figure out how much energy we get back when we form them again. And so unlike enthalpies of formation, if we have bond enthalpies, it's actually the opposite way around. And what they'll do is they'll give you a chart of all of the values that you could potentially need. So they'll tell you this is how much a C to H bond is worth. This is how much a C to O bond is worth. And then what you do is you figure out the sum of all of the energy it takes to break all your bonds, and then subtract it from all of the energy that you get back when those bonds are formed. And the reason it's the flip-flop or the reverse of what we did before is because when we look at bond enthalpies, they're generally positive because they're trying to figure out how much energy it takes to break it. So when you look at those values, they're positive. So we have to think about bonds broken minus bonds formed so that we get a negative value when our bonds are forming, that math part, because it's exothermic. So when you think about this, it's reactants minus products. And frustratingly, this equation is not printed on the exam. So you got to keep this in the lockbox up here that you remember that it's enthalpies of formation are products minus reactants, and that's printed on there. And bonds are the flip-flop of that. You see it all the time that people get those things mixed up. So we're going to go straight into examples because I think that it makes things make more sense when we do this. So this is, you'll see me starting to kind of grab questions more from the AP exam because we're really digging into some of the deep meat of the exam. That sounds kind of gross, but that's what we're doing. So anyways, fulminic acid can convert to isocyanic acid according to the equation below. And they give you the equation here. They tell you what fulminic acid is. And understand that this was part of a big part of the question. So there were other parts to this as well. So it says, using the Lewis structure diagrams of fulminic acid and isocyanic acid shown in the boxes above, and the table of average bond enthalpies below, determine the value of delta H for the reaction. So again, reactants minus products. So what we need to do is we need to analyze all of these bonds in here and then do that math. So that is where we're headed here. Okay. So like I said, you're not going to be expected to know those values. It's not like standard enthalpy of formation where any values are zero. Everything has a number value here. And so in this case, we got to think about it as reactants minus products. Okay, so it's R minus P. And so we're going to go from fulminic acid. This here is our reactants, and this is our products. And I would honestly recommend kind of just really writing all over your test to keep it clear, because otherwise it can be really easy to mess this up. So when I'm looking at this process here, I got to look at the connections. So I've got if we look at our balanced equation, it's a 1-to-1 mole ratio. And that means I don't need to multiply anything by a coefficient of 2 or anything like that to worry about. So these, like I said, are pretty simple Lewis structures. I have a C to H, a C to N triple bond, and then an N to O single bond. Then I have N to H single bond, a double bonded nitrogen to carbon, and a double bonded carbon to oxygen. So they give me all of these values here, and I'm going to work with them. In this case, I am not going to be quite as fussy with the units, but I do want you to keep track of the bonds so that you are mentally keeping tabs on them. So I've got a C to H here. I got to find that, and that's 413 kilojoules, okay, plus 1 C to N, so that's going to be 891 kilojoules, and then I'm breaking an N to an O, which is 201 kilojoules. Okay, so I have here, and technically it's kilojoules per mole. Okay, but if you think about this, so this is my C triple N, and this is my N single O bond here. When you look at these, as long as you have the kilojoule value, there is that 1 mole of bonds that you're breaking kind of out front here. So if you leave that off, it's not the end of the world, in my opinion. And the other one, you got to be a little bit more careful about it. But with these bonds, honestly, it can be super hard to keep track of. So I don't do it as much. But technically, if you want to be really down with it, it should be 1 mole of CH bonds times 413 kilojoules per mole. But like I said, that can be a little icky and hard. So I've got all of this here. And then if you think about it, that means that to break a mole of the C to H bonds, I've got to put in 413 kilojoules. To bust up all of these triple bonds, I need to add another 891 kilojoules. And then to break those N to O bonds, I got to have 201 kilojoules coming in. Okay. Now, is that how that happens in reality? Maybe not quite as much, but the math is what we're going to kind of follow here. So those are my reactants. Now my products, I'm making an N to H bond. So for N to H, when I make that bond, I get a pretty nice chunk of energy coming back into my process. So when I reform that bond, I get 391 kilojoules from that 1 mole of N to H bonds being formed. Then I'm making a C to N triple bond, or I'm sorry, double bond. And that's going to give me back another 615 kilojoules. And then I'm going to get back a mole of the C to O double bond, and that's going to be 745 kilojoules. Okay. So if you think about it, this is all the energy I put in. This is all the energy I get back out. And if you think about our graph, this is the rise, this is the fall of our graph. And so if we do those totals, I get 1,505 kilojoules that I need to get in to break all of those bonds. And then I get back out 1,751 kilojoules on the end. So I'm, in this case, my overall enthalpy change is negative 246 kilojoules worth of energy. So that's an exothermic process. And if you think about our graph then, we start, we go in, and we end lower. Maybe a little dramatic there, but that's what we're looking at, okay? So I put some energy in, put a decent chunk of energy in, but I get a good chunk out on the back end as well. Okay. Now this one's gonna be a little bit harder for you maybe to copy down. And this isn't necessarily a question that you're gonna see on the FRQ section quite as much, but I've seen questions like this on the multiple choice. And what I think is interesting, and maybe not this complicated, but what I think is interesting is that if they give you the structures already, sometimes you are going to notice that not everything is different on your reactant side to your product side. So if you look at our energy values here, we have C to O bond is 745. We got the C to O bond for CO2 though, a little stronger, and it's 799. We've got N to H's, we've got O to H's, and we've got a C to N. What we also have in this problem is a coefficient. So this means that I technically have 2 NH3s that I need to bust up. So you can either mentally keep track of that, or if it helps you, you can draw out another NH3 to kind of keep you in line here. But what I think is going to be important is taking a look at what is the same in these, because some of this is the same. Now we have 2 C to O double bonds, but it's in CO2, and it's established down here that those are different energy values. So that's not anything we can cancel out. But if you look here, I have 6 N to H connections that are single bonds on my reactant side, and I've got 4 of them over here on the product side. So when I do my math and I kind of pay attention to those values, I can almost kind of treat this like a Hess's law problem, where these guys on my product side here are kind of gone and cancel out with 4 of the NH bonds on the opposite side. And what I'll see sometimes on the multiple choice section is they'll kind of ask you to do this mental math a little bit, and then they'll ask you to kind of figure out what's different and what's the same without using a calculator. And it helps if you can visualize what is going away. So we'll do this math now. So I've got 2 C to O double bonds from carbon dioxide. So I'm going to put 2 here now because I got 2 of them, times 799 kilojoules. Okay. And like I said, it's technically kilojoules per mole, but they will accept not having the mole part there, and they will not lose any sleep over that. So I've got the 2 times 799 plus now just these 2 NH3s here. So 2 times 390 kilojoules. That's kind of a dramatic parentheses, but that's okay. And then we're going to subtract the products, which have 2 C to N's. And like you can kind of even see here, it's easy to lose track of what you're up to, and I kind of forget stuff. So I think it's really important to keep that, because when you go back and look at this later, you're like, where did those numbers even come from? So I've got 2 C to N's. 2 times 290 kilojoules, because I'm breaking 2 bonds of those, okay? Plus, then, I'm not breaking, I'm sorry, I'm making those. So I have a C to O that's not in anything. Okay, and then I'm making 2 O to H bonds. Okay. So this is my C to O double bond that's not in CO2, and then I've got O to H as well. And again, this can be really tricky. It's easy to miss stuff, so you just have to be kind of careful with what you're doing here. So if I take these numbers and I put them together, I get 2,378 kilojoules that I have to put in to break up this stuff. Now, technically, I've got to put in more, but what's going to happen is if I break these 4 NH bonds, they're going to make 4 identical bonds on the other side, and so I can ignore them. So then it's minus 2,253 kilojoules in this case. And so my enthalpy change is going to be positive 125 kilojoules in this case. So that means that in this case, I got to put in more energy to break than I get back out. And so this is an endothermic graph. Okay, my delta H is the difference between these 2 points here, and that's a positive 125 kilojoules. Okay, so hopefully this makes a little sense. The biggest thing is that you need to remember reactants minus products for bonds, because that's not on your equation sheet. Okay, now it's time to practice. If you find yourself having any questions, please let me know. Otherwise, good luck to you.